Welcome back to Mr. DuPage's classroom. This lesson is for my Algebra 2 class. It is 7.2, Day 1. Use combinations and Pascal's triangle. Combinations, selection of R objects from a group of N objects where the order selected does not matter. So say there's 30 people in a room. I ask 4 of them to go run to the office for me because there's 4 things down there that need to be picked up. I don't care who leaves the room first, second, third, or fourth. I just need 4 of the 30 people to go down there and take care of the situation for me. So in that situation, what would happen is that I would have 30 people in the room. I need a combination of 4 people to go. So if you're looking at the formula up here, I have 30 combinations of 4, or 4 combinations of 30 really. So the n factorial is my 30, so it'd be 30 factorial, over, now I use n minus r, so it'd be 30 minus 4 factorial, times the r factorial. What this is doing for us, this is the only thing that changes from our permutation formula. The r factorial gets rid of the order, the order mattering for us, okay? So what I would do here is I'd have 30 factorial over. I'd go ahead and work my way through that problem. I just wanted to show you with an example as we talked about the formula exactly how it would work, okay? So now we need to find the number of combinations, 6 combination 5. So it'd be 6 factorial over 6 minus 5 factorial times 5 factorial. Because 6 is my n, 5 is my r, right? So here, I need to simplify, so I have 6 factorial over 6 minus 5 is 1 factorial, and then I have 5 factorial. Just like the last couple of sections we've gone over, what I'm going to do is I'm going to write out my numerator until I get to the largest factorial in my denominator. So I have 6 times, 5 factorial is my largest factorial in my denominator, so I'm going to stop there. Then I have 5 factorial. You can get rid of those. I technically have 1 factorial, but that's just 1 times 1, right? So I'd have 6 over 1, which is 6. Okay? On to problem 2. 9 is my n. That's the total number of objects I have, the total number of people I have, however you want to look at that. So I have 9 is going in my numerator. Then I need groups of 4. So I'm going to take 9 minus 4 factorial times 4 factorial. If I simplify my parentheses there, I have 9 factorial over 5 factorial, 4 factorial. At this point, again, just like I did in the last problem, I want to go ahead and write the 9 factorial out until I run into the largest factorial, which would be 5 factorial. So it would be 9 times 8 times 7 times 6 times 5 factorial over this would be 5 factorial, and then I'd have 4 times 3 times 2 times 1. The 5 factorials can go away. Well, 4 times 2 is 8, so if I get rid of the 4 and the 2, make that an 8, the 8 and the 8 can go away. This 3 and 6 can simplify the 6 into a 2, so now I have 9 times 7 times 2. 9 times 7 times 2 would get me 126. If you do not like the simplifying of the 4 times 3 times 2 times 1, you just want to get rid of the 5 factorial and then multiply your numerator out, then multiply your denominator out, and then take that as a division problem, you can go ahead and do that. That doesn't bother me at all. I'm just trying to show you a way to simplify things down first before you have to actually multiply. Now I have 10 combination 7, so it would be 10 factorial over 10 minus 7 factorial, 7 factorial. Remember that 7 has to come out again. We have to use 7 factorial to get rid of the order mattering. So if I simplify this, it'd be 10 factorial over 3 factorial, 7 factorial. Do not multiply or add those factorials in the denominator. We do not want to do that. But again, I'm going to write my 10 factorial out until I get to my largest factorial in my denominator, which is the 7 factorial. So it'll be 10 times 9 times 8 times 7 factorial over 7 factorial. Now I have to work with my 3 factorial. That would be 3 times 2 times 1. Get rid of the 7 factorials. 3 can simplify with my 9, turns my 9 into a 3. 8 and 2 turns my 8 into a 4. So now all I'm multiplying together is 10 times 3 times 4, which would get me 120. Okay? Now, you guys won't be real happy with me, but there is a way to do all of this in a calculator. There'll be times that I tell you you must show your work. When you must show your work, you must do what we have done by hand every single time in the first couple sections. If it just asks you to solve the problem, then you can use the calculator. I'm going to go ahead and cut to where I have my calculator open real quick, so bear with me. Okay, now that I have my calculator open, we can go ahead and work through some of this stuff. So find the number of possible 5-card hands that contain the cards specified. The cards are taken from a standard 52-card deck. If you do not know what a standard 52-card deck looks like, you need to ask me. We'll try to bring in a deck of cards with me tomorrow to make sure that you guys can see exactly how they are laid out and how they work. But if you don't know what a deck of cards looks like, you really need to ask me. So a deck of cards is split into 2 colors. You have a set of black cards and a set of red cards. They each have 26 cards in them. So 5 black cards. I need to find the possible 5-card hands of 5 black cards. That means there's 26 black cards available. It did not say anything about the order of my hands. So since we don't care about the order of our hands, what we're going to do is we're going to use combinations. So to be 6, combination 5. This is where the calculator comes into play. Now that I know what my combination problem is, what I can do is go to my calculator. If you're using one of my newer calculators, you're going to hit Math. You're going to go to the right, and you're going to find Probability. We're going to go down to NCR and hit Enter. Oh, I'm sorry. The first thing we need to do, actually, is type in our number 26, then go to Math, Probability. Then I'm going to go down to NCR because we're using combinations. And then I'm going to put 5 as my second number and hit Enter. It's going to come up with the answer for us, which is 65,780 different combinations. So if I go back, there are 65,780 combinations of 5-card hands I can make with just black cards. Okay. Now, problem 5 says I need 3 aces and 2 kings. There are 4 aces in a deck, and there are 4 kings in a deck. In fact, any card that you hear about, if it says 9s, 10s, jacks, kings, queens, aces, 2s, they all only have 4 cards. Okay? So this is going to be a combination, and this is going to be a combination. So let's write out our combinations first. I have 4 aces. I need a combination of 3 of those. I have 4 kings. I need a combination of 2 of the kings. Now the word that gives away exactly what we're going to do here is the word and. If it says and, that means they both have to happen. Okay? And if they both have to happen, what we're going to do is multiply this together. So again, if you use your calculator, you'll figure out that 4 combination 3 is going to be, there's 4 combinations of possible aces. And then for the possible kings, there would be 6 combinations of the kings. 4 times 6 would get me 24. Again, to use this in my calculator, what I'm going to do is I'm going to type the number 4. I'm going to go to Math, Probability, go down to Combinations, and then type in 3. And that told us there are 4 combinations, which we already knew. Okay? On to 2 face cards and 3 cards that are not face cards. Face cards, there's only 3 types of face cards in a deck. There are jacks, queens, and kings. I told you that every type of card has 4, so 4 times 3 would get me 12 face cards. There are 52 cards in a deck, So the next part is asking me for 3 cards that are not face cards. So I'm going to take 52 minus the 12 will get me the 40 cards that are left over. So my first combination is going to be 12. Out of the 12 cards of face cards, I need 2 of them. And then out of the 40 cards that are not face cards, I need 3 of them. Okay? So those are our 2 combinations we're going to look at. My first combination would be 12, combination 2. Again, the word and is here, which means I'm going to multiply. So then I have 40 combinations of 3. Well, 3 combinations of 3 from my 40 cards is really what that is. Again, if you use your calculator, what you're going to find out is the possible face cards that I have would be 66 combinations of face cards. The number of combinations of non-face cards would be 9,880. So 66 times 9,880 would get me 625,080 possible combinations total between the 2 groups of combinations that I'm looking at. Okay. Problem 7. Now we have red cards and black cards. We already talked about the fact that there's 26 black cards in a deck, which means there's also 26 red cards in a deck. Basically, anytime you see a color, take 52 and divide by 2. That'll tell you how many red cards are possible or black cards are possible. Here, there's a different scenario, though. I have the word or. Okay? So here we need to be a little bit careful. But my first combination is the 26 red cards, and I need 5 of them. So I have 26 combination 5. Same thing with my black cards. I'm going to have 26 combination 5. Now the word or says I can have either 5 red cards or 5 black cards. So it doesn't have to, both the situations do not have to happen. So I'm not going to multiply. What I'm going to do here is add. So when you see the word and, it is multiply. When you see the word or, you're going to add. All right? So again, if you use your calculator for your combination calculations, you end up with 65,780 plus 65,780, which would get me 131,560 different combinations that are possible. Okay? Now, diamonds, there are 4 suits. They are diamonds, clubs, spades, and hearts. So if I take 52 divided by 4, what I'm going to find out is every suit has 13 cards. We already know that the black cards, there's 26 of them. And again, I have the word or. Okay? So I need 5 cards, 5 of the diamonds in some combination, right? So it'll be 13 combination 5 plus, because of the word or, then I have a combination of 5 of my black cards, so 26 combination 5. Here again, what I'm going to do is use my calculator. I find out that 13 combination 5 gets me 1,287 plus I need 5 cards that are black, so on my second combination I end up with 65,780 possible combinations. If I add that up, I end up with 67,067 possible 5-card hands that I could have. Okay? Moving on. You are on vacation and can visit as many as 5 cities and 7 attractions. Those are your total numbers. You have 5 cities, 7 attractions. Those are your maximums that you're going to use for your combinations. You want to visit 3 different cities, so 3, and 5 different attractions, so 5. Also, notice I have the word and, so that should help us out. How many different trips are possible? Did it ever say anything about I have to go to this city first with that attraction, or did it ever make any mention of order being a difference? Well, no, it didn't. So what that means is I'm going to use combinations here. So the first combination is my 5 cities and my 3 cities. I have to choose 3 of my 5 cities. So it'll be 5 combination 3. I have the word and, which means I'm going to multiply in between. Now I have to choose 5 of my 7 attractions. So it'll be 7 combination 5. Okay? If I use my calculator here, I find out that my 5 combinations of 3, or 3 combinations of 5 is 10 different combinations. Then the number of combinations I can have of the 5 different attractions from my 7 attractions, I'll find out that there's 21 different combinations of that I can use. So 10 times 21 would be 210 different trips that I could take. Okay? Suppose you want to visit at least 8 locations. Well, the number of locations is going to be my 5 cities plus my 7 attractions, so it'll be 12 different locations. How many different trips are possible? I want to visit at least. A couple things happen here when I see the words at least. First thing is, this is going to be an OR problem. So I know I'm going to add in between my combinations. The second thing is, I have a lot of choices here. If I want at least 8 locations, well, I know that there's 12 possible locations, right? So to choose 8 of them, I would have 12 combination 8. But it says at least, so that's the minimum I'm going to do. So the next thing I need to find out is combinations of 9 locations. Then combinations of 10 locations. Then combinations of 11 locations, and finally combinations of 12 locations. Since it said at least, it didn't say that I couldn't go to all 12 of them. It just said that I want to go to at least 8 of them. So I need the combinations for just 8, I need the combinations for just 9, the combinations for 10, the combinations of 11 places, and the combinations of 12 places. If I use my calculator to figure all this out, I find out there's 495 combinations of 8 locations. There's 220 combinations of 9 locations. There's 66 combinations of 10 locations. There's 12 combinations of 11 locations. And there's 1 combination of 12 locations, which makes sense because there's only one way, if order does not matter, to go to 12 places, and that's just to go to 12 places. If I add all of that up, I end up with 794 different trips that I could take. Okay? A club at your school has a president and vice president. The club has 15 students. In how many ways can students be chosen for the 2 positions? Here you need to be careful. Say that I chose, there's Johnny and Jamie that are in the club, right? Johnny and Jamie are in the club. Johnny can be the president, and Jamie can be the vice president. At the same time, Jamie could be the president, and Johnny could be the vice president, right? So the order between those 2 different situations has changed, and it does change the possibility, right? So if it's talking about having a club with specific positions, like president or vice president, president, vice president, secretary, then order matters because of the specific positions that are available. If it just said a committee of 5 people, the order would not matter. I don't care who got chosen first, second, third, fourth, or fifth. They're all at the same level. But if there's different levels of the committee, like president, vice president, secretary, then that would change to order mattering, right? So since order matters, I'm going to have to use permutations. So I need to know how many permutations are there of the 15 students chosen for the 2 positions. We write it just the same as we did for the combinations, right? The whole group comes first, then I have my permutations, then the number of positions I'm looking for comes second, right? Well, just like with combinations, if I want to use permutations, I can use my calculator. 15 is the number of people. Go ahead and go to my math button, over here to probability, and PR, how many positions were there? Well, there were 2. Hit enter, find out that there are 210 different ways or permutations to choose the president and vice president from 15 people. Okay? Now this says on your own. What we'll do is we will go over this when you guys come into class tomorrow. But what I want to show you is it says show your work. This is the situation where you cannot use your calculator. You must write it out like we did on the front, examples 1, 2, and 3. Okay? Then you have a couple of story problems. We have some card problems, which we have gone over. If you have any questions about cards, find the number of possible 5-card hands that contain kings. There are 4 kings in a deck, and there are 4 aces in a deck. That should help you a little bit. The manager of a chain restaurant must choose 6 restaurants from the 11 he owns for remodeling. How many different ways can the 6 be selected? Think about whether order matters there or not. Did it say that this restaurant has to come before that restaurant? Well, it didn't, so think about that, okay? I want you to try those on your own. Bring them with you tomorrow. Otherwise, the most important thing to remember here is that combinations, the order does not matter. Here is our formula for combinations. Make sure that you know that, okay? If you need some help about the number of different types of cards there are in a standard 52-card deck, please come in and see me. Otherwise, thank you very much for watching the video, and have a great day.